Hi, I'm Randall Heyman. This is my 160th Corona Help video. If you'd like me to make a video for you, then comment below any of my videos or drop me an email. Before coronavirus, I actually made about 60 videos that are made in a better way with animation software. And so have a look at them if you're interested. And in particular, it's relevant today because we're going to be talking about Lagrange multipliers. And if you're not familiar with the gradient of a function, and here I'm talking about a two-dimensional, three-dimensional function, I really should say 2 or 3 variable function. If you're not familiar with that, then you should have a look at that video, Gradient of a Function Made Easy. So today we're going to talk about Lagrange multipliers for Balthazar. So, pardon me, let's look at a problem and I'll go through it so you understand why this works as it should. I'm going to take an example from one and several variable calculus by Salas and a couple of other authors. Pardon me. That's better. Normally I don't use examples from books, but today I will. It's getting very close to Christmas, so I'm nearly done for the year. Okay, so let's write this up. So we want find the minimum and the maximum of fxy equals x times y on the unit circle. And the unit circle is x squared plus y squared equals 1. Okay, so what are we going to say about this? Well, the first thing is, if you think about minimizing and maximizing, you probably will have learned that there's a few conditions that we need to first clear up that ensure that there is in fact a minimum or maximum. In some situations you won't get a minimum maximum. For example, if fxy is not continuous, well then you may not get a minimum or maximum. And similarly, if in this case the unit circle is closed and bounded, so that also ensures that we get minimums and maximums. So if you were going to do this properly, you would say, firstly, f is continuous and the unit circle is closed and bounded. So I'm not going to say any more about that and we'll launch into it. Obviously, if you've got any questions on any of this stuff, you just come back to me by commenting or emailing. Okay, so what we'll do is we'll say minimum, minimize or maximize. Actually, why don't I draw a bit bigger, write a bit bigger. Minimize and maximize f, x, y, subject to a condition. And the condition is to g x, y, which I'm going to call x squared plus y squared minus 1 equals 0. Okay. So that's the task that we're about. Okay, now let's look at a graph, because this will give you the understanding, I hope, of what's going on here. Okay, and this is where you'll need to know about the gradient of a function. Let me put that there. Okay, so let's start drawing. So I'll start by just drawing the xy here. Okay, so let's label that y and x. Now, let's put on the unit circle. So this is the G part. I'm going to do that in red, and I'll do it, if I go like there, and go like that, I should get, whoops, no, it's not going to work. I should have drawn this beforehand. Okay, I'm just going to hand draw them. Doesn't matter, you'll still get the idea. Okay, here's g xy equals 0. Okay, and now let's draw some of the, we don't know what fx is. Actually, let's just draw up here just so you remember fx equals xy. So the curve xy could be, you know, it could be like this. We don't know the level. They're all hyperbolas, but so this is, you know, fxy equals, I don't know, that might be 2, and this one might be, I don't know, doesn't really matter. Fx equals 1, doesn't matter. But there'll be different levels here as we fill it in. Okay, now the gradient of the function, if you like the slope of the function, and here you should go back to my video if you're not sure about how this works, but let's start drawing on some gradients. The gradients here go like this. Like that. So they're perpendicular to the curve and going out. And we can do the same thing with the unit circle. Now, remember, the idea is to get the maximum value of f as we go along this circle, unit circle. We can consider out we're just walking along here. So if I actually draw, here's a point here. In fact, let's draw down here. Let's start down here, down here. So if I asked you what's the gradient here of the circle is that, and the gradient of the of f, the hyperbola, is here. So they're not the same. And what that means is that, and you can see here, well, you're better off to just keep walking along here. You're better off to keep walking along this unit circle, because there's always, if you like, you can walk up the slope on these. You can walk up the slope as you go. But you get to this point here, and at this point here, an interesting thing happens. Both of the gradients, well, the gradients are parallel. And at this point here, there's no point going on further. If I go on further, you can see I'm actually going lower down the fxy curves. If once I get down to here, my value of xy is only this amount here. I want my value to be as high as possible if I'm going to find a maximum. And so that happens here when when the two gradients are actually perpendicular. Okay, so that gives us an understanding of what we need to do. So let's just leave that there so you can just see that. And let's go to black now. And so what we've got to do is, so we've got, let's just write it up here again. fxy equals xy, g xy equals x squared plus y squared minus 1. So now what I'm going to do is I'm going to find the gradients and make the gradients parallel, essentially. Okay, so let's work out the gradient of f. Well, to do that, you take the partial derivative of this with respect to x, so you get y, and that acts in the direction of the x-axis. And if you take the partial derivative of this with respect to y, you'll get x, so that's xj. If you do the same thing with g, you'll take the partial derivative with respect to x, 2x in the direction of I, and the partial derivative with respect to y is 2yj. Okay, so we now set the gradient of f is going to equal lambda of the gradient g. That's just ensuring that the two gradients are parallel, which is where we have a minimum or a maximum. So if we now equate the x, I suppose the I we have y equals, and here we have x. So y must equal lambda by 2x. And if we equate the j's, the j direction, the j vector, here we've got x equals lambda times 2y. So this one I'll multiply by y squared equals lambda 2xy. This one I'll multiply by x squared equals lambda 2xy. These two are the same. So I'll get x squared equals y squared. Also, so that's good. We know that x squared must equal y squared if there's going to be a minimum or a maximum. And also, we know on the unit circle, because remember, we must stay on the unit circle. We're finding the minimum or maximum there. X squared plus y squared equals 1. So we've got that equation and that equation, two equations, two unknowns. If you solve that, you'll get that x, well, you'll only get, there's only 4 points. So xy could be, well, we could have the point 1 on root 2, 1 on root 2. And that's where if we go back to here, that's that point there. That's 1 on root 2, 1 on root 2. But of course, the unit circle and the hyperbolas go across here as well. Here's the hyperbolas, here's the circle, blah, 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 all around. So there's actually 4 points. So let's just keep going. So it could be that, or it could be 1 on root 2, negative 1 on root 2. These are all solutions of those two equations. So that's another point. It could be negative 1 on root 2, 1 on root 2. Or finally, it could be negative 1 on root 2, negative 1 on root 2. Okay, so the last thing is, how do you work out which are minimums or maximums? Well, you actually work them out. So here, fxy, sorry, I'm really writing really badly. Let's get rid of that for a sec. So here, fxy is equal to 1 on root 2 times 1 on root 2, which is equal to a half. Here, fxy equals negative a half. This one's a maximum, this one's a minimum. Fxy equals negative 1 on root 2, negative a half. That's also a minimum. And finally, we have the second maximum, which is fxy, sorry, which is equal to x times y equals a half. So we've got 2 minimums and 2 maximums. And if you go back to the circle, what would happen if we took this point here? That's on the unit circle, but here, fxy is equal to x times y equals to 0. So you can see that point is neither a minimum or maximum. It's between negative a half and positive a half. So everything sort of at this stage seems to be working pretty well. So that's Lagrange multipliers. You've got there the basics on how to do a question. I've actually done a question, but hopefully through my explanation, you've also got an understanding of why it works as well. Okay, any questions, comment or email me, and if I think I can help, I will do so.